We're in chapter 1, page 1. And what we're going to study this morning, what we're going to look at this morning is measurements. That is the heart and soul of science, is what we can measure. I had an undergraduate professor who explained it this way. He said, whatever you can measure, that's physics, that's science. Anything beyond that is theology. Now, that is more true than any of you probably have ever thought about or imagined. Let me ask a question. Who here can tell me who was the first scientist? Somebody, anybody? Galileo Galilei. He was the very first scientist. What made him a scientist? He did experiments. And that is the nature of science. The scientific method is really profoundly simple. You start with a hypothesis, you test it experimentally, and once you have confirmed it with experiment, it is proven. It's knowledge, which is the literal meaning of the word science, is knowledge. If you cannot prove it experimentally, it doesn't matter how many people agree with you, it's not knowledge, it's not science, if it's not experimentally proven. Long before Galileo, there were lots of people that you probably think of as early scientists. Plato, Aristotle. But they were not scientists because they did not conduct experimental proof of their hypotheses. They simply observed the world around them and thought about it. They developed consensus, but they did not prove anything. You've heard of the Ptolemy, right? You've heard of him? Maybe, maybe not. How about this fellow, Democritus? Who's heard of Democritus? And no, he has nothing to do with government. Democritus was born in around about 400 BC. He was born in 460 or 4 something BC. Died right in 300 and something BC. He introduced what we now call the atomic model. Democritus postulated that for any piece of matter, for any element of matter, you could cut it in half and you would have 2 pieces of the same stuff. And if you cut each of those pieces, you would have even smaller pieces, and you could keep cutting it down to smaller and smaller pieces until at some point you would get to a point where if you had a piece of that matter that was so small that if you cut it into 2 smaller pieces, they would no longer be the same stuff. Now you would be working with whatever the original stuff was made of. Now, because he was Greek, he spoke Greek. So what he called his postulate was not cuttable. But because he spoke Greek, he pronounced it atomos, or what we derive the word atom from. Okay? This was 400 BC. Galileo didn't come along till, 1600s? Something like that? AD. There's 2,000 years separating Democritus from Galileo. But Democritus was not a scientist. He was, like Aristotle, like Plato, like Ptolemy, he was a philosopher. And he was right. That's why we call these fundamental quantas of matter atoms today, not cuttables. But he still didn't prove his postulate. He didn't prove his hypothesis. He just thought about it and decided this is what he believed. And that's the difference between science and philosophy. It's about what you believe as opposed to what you can prove, what you can empirically know. Ptolemy had a model of the universe where the earth was at the center and everything else, Mercury, Venus, the sun, the other planets, and all the constellations of the stars, all circled around the earth in great giant orbits. Now we think of it that way today and we think, well, that's just silly. But think about it from his perspective. When he looked up at the night sky, that's what he saw. Planets and stars moving in big circles. And the stars in constellations, which did not move relative to each other, but the whole constellation that moved in great circles. The word planet derives from the Greek word planete, which means wandering star. Because the planets didn't move the way stars moved. Where the stars sweep out these big giant circles, the planets would just cut a line, a big arc across them. And so that's where how many of you have ever heard the expression of hitching your ride to a wandering star? If you try to navigate the oceans on a sailing vessel, you use the North Star as your guide, you'll be able to get right where you want to go. But if you try to use one of the planets as your guide, then who knows where you're going to end up. Even back then, they noticed something in the motion of the planets called retrograde motion, where the planet will start moving across the sky, but then it'll stop, and it'll back up a little bit. And then it'll stop, and it'll start going in the other direction again. They had no idea how they did that or why. They just knew that they saw them do it, so they could. By the time Galileo came along, it was fairly well accepted that there were two realms of physics, of motion. That there was the laws of celestial motion and the laws of terrestrial motion, how things move on Earth, on the planet. They decided that the natural state of objects in the celestial realm was to move in perfect circles. And they decided that the natural state of things on Earth was to not move at all, was to stop, to stay motionless. Then along comes Galileo and Copernicus and a bunch of actual scientists who started doing experiments to try and verify their ideas. What Copernicus introduced was he went from the geocentric model, Earth-centered, to the heliocentric, or sun-centered. And in his model of the universe, everything in the universe revolved around our sun. Why did he introduce this major shift in thinking? Well, because of that retrograde motion. See, somebody had come up with the idea that since the natural motion in the celestial realm was in perfect circles, that you could explain retrograde motion and motion of the planets when you started putting littler circles superimposed on the big circles. And then you could correct it again by adding even tinier little circles to the motion of the planets and the star, to the celestial motion. Now, just honestly, how many of you think that sounds kind of stupid? That's like, well, they're really grasping at straws. How many of you have heard of the mathematician Fourier? Fourier introduced the theorem, which is proven, that you can describe any arbitrary function as the infinite sum of sine and cosine functions. What are sine and cosine functions? Little circles. Okay, my point that I'm trying to make here is that be careful when you look back at these old philosophers, and what they thought of, what they came up with was not science, but it was not always wrong. And we are not always as right as we think we are. Consider Copernicus. He went to the heliocentric model because he figured out that if you look at everything as orbiting around the sun, then that will change how the motion appears on this planet, how this planet's motion will appear on this other planet when they're both moving relative to something else. And to that extent, he was right, and he was much closer to what we now call the truth. As you get further into physics, you're going to learn that, and especially if you go into astronomy, you're going to learn that, in point of fact, they're both wrong. That the sun and the planets do not orbit the sun. The planets and the sun both orbit a point in space that is the center of mass of the total system. That's how we are able to find planets in distant galaxies, in distant solar systems. Not because we could see the planet, but because we could see the wobble of the star as it wobbled back and forth, telling us that there's something orbiting it. Galileo did his most famous experiment when he dropped two objects from the Leaning Tower of Pisa, the first actual experiment. Now, intuition would have suggested that the heavier object would fall faster, the lighter object would fall slower, that the heavier one would hit the ground first. What he discovered was that they both hit the ground at the same time. And that nothing could better highlight the importance of experimental confirmation in the scientific method. Doesn't matter how smart you are, it doesn't matter how much thought you give something, it doesn't matter how firmly and deeply you believe something to be true. Experiment can always surprise you. And that was a perfect example. No one would ever have guessed that both objects, the heavy and the light, would both fall at the same rate. And what he proved was that the heavier object and the lighter object were both accelerated at the same rate. Now, we would later come to find out, well, the force acting on the heavy object was greater than the force acting on the lighter object, but they both accelerated at the same rate. I don't want to get too far afield. Even Copernicus, touching on this one more time, even Copernicus with his heliocentric model, he still had the constellations orbiting the sun. Okay? Galileo did another experiment that just fundamentally changed everything. Remember, at the time he came along, there were two, basically, the consensus was that there were two realms, celestial and terrestrial. Natural state of motion in the celestial realm was everything moved in perfect circles, or sums of perfect circles. But on Earth, the natural state of motion was at rest, was to be motionless. Well, what Galileo did was he conducted an experiment where he took a a ball on a piece of track, and he started it here, and he let it drop, and it rolled down the track, and it rolled back up to the same height it started from. And he thought, okay, well, that's a measure of how far it will move, based on its acceleration it gets as it falls. Well, then he repeated the experiment where he made the track longer. And he thought, well, here it moved this far, so here it's only going to move that far and stop. Because that's the natural state of motion in the terrestrial realm, is to be at rest. Well, again, his result shocked him, surprised him. Because the ball didn't stop, it kept on going, and it went all the way back to the same height that it started from. The same ball, but this time it went further. It traveled a greater distance. What Galileo then did was, and he was able to conceptualize the loss of energy to friction, and he was able to idealize, because he had done that in his gravity experiment, because if he realized that you had to eliminate the air resistance as a factor in order for both objects to accelerate the same. If you try that experiment with a hammer and a feather, the hammer is going to hit the floor first, because you cannot neglect wind resistance on a feather. Well, here he was able to conceptualize away the friction, the losses of friction due to the contact between the ball and the track, but he proved that the distance the ball went was irrelevant. And in fact, he conceptualized that if he then took the track and did not raise it on the other end and just let the ball go, that the ball would continue moving until it was finally brought to rest by losses to friction. This was a sea change moment. This was what we call a paradigm shift in the way people think, because he realized, what he proved empirically was that the natural state of motion is not at rest. The natural state of motion in the terrestrial realm is to remain in motion, unaccelerated motion. What does that word mean, unaccelerated? We think of acceleration in relation to the cars we drive. So we think accelerate means to go faster, and decelerate means to slow down. In fact, acceleration is any change in velocity. Does everybody here had, that's a question I want to ask. How many people here have had calculus? Oh, okay, there's quite a few of you. I take it you've all had at least trigonometry? Okay, you know what vectors are. Good. Any change in the velocity is a vector. It has magnitude, speed, and direction. And any change in that velocity vector, whether it's a change in magnitude or a change in direction, is an acceleration. Galileo proved in this experiment that the natural state of motion in the terrestrial realm is unaccelerated, is zero acceleration. It's unaccelerated motion. Whatever motion you have, you will keep until something stops you. But he still had the notion that there were two separate realms. Who knows when that changed? Any guess? Here's a hint. The natural state of motion is unaccelerated motion. An object in motion will stay in motion unless acted upon Isaac Newton, his laws of motion. He didn't invent them. All he did was restate what Galileo had already proven. Now, he came up with some really brilliant insights, in particular the thing with with the apple falling from the tree and introducing gravity. This was the great accomplishment of Newton. Not that he came up with his laws of motion. What he did was he reconciled the celestial, I don't need to write those out. He reconciled the laws of celestial motion with the laws of terrestrial motion. And in some point in the semester, we're going to do a lab on gravity, and you're going to learn. What he was able to conceptualize was the idea that if the Earth is a giant sphere, and you start up at the top of a tall mountain and you throw something, gravity is going to pull it down. But if you throw it again faster, it'll take longer for gravity to bring it down. And if you throw it fast enough, it'll come all the way around to here in the time it would have taken, that it simply will never fall down. He conceptualized orbital mechanics, the basis of orbital mechanics, sitting under an apple tree in medieval Europe somewhere. He unified the two sets of laws, celestial motion and terrestrial motion, so that he was able to show that all motion in both realms is governed by the same set of laws, that nothing changes. The only thing that changes is our perspective of that motion. What does that sound like? Somebody? Anybody? Take a guess. What does that sound like? That all motion is relative to your frame of reference? Now I'm getting ahead of, I'm not getting ahead of the class, I'm getting ahead of this whole course, because that relativity comes in at the end of physics 2. So we're not going to get there today. But the point is what he did, what Galileo did was introduced experiment and the scientific method. What Newton did was unify what had formerly been considered diverse sets of laws governing diverse sets of motion. In the textbook here, it talks about models, theories, and laws. And I do want to touch on this a little bit because it is important for you to understand this. What is a model? What is a theory? And what is a law? And a theory is a concept, an idea, a hypothesis. I think this is how it works. I believe this is how it works. But this is the crucial point. In order for a theory, a hypothesis, to be a scientific theory, it must produce quantifiably testable predictions. That is a fundamental tenet of the scientific method, that the ultimate test of any hypothesis is its ability to predict future events. Okay? If a hypothesis is not testable, if no experiment can be conducted to confirm it or to refute it, then it's not a theory. It's not a scientific theory. It is just a guess, an idea, a philosophy. Maybe it's right, maybe it's wrong, and as we've seen, until we can test it experimentally, we really don't know, because one lesson we have learned repeatedly over and over and over again is that we will be surprised, we will be shocked, our worldview will be shattered. What we deeply believed with all of our heart was the truth was proven wrong. Models are Well, a model is just an analogy. It's a way of thinking about an abstract concept in terms of something that we can wrap our minds around, something that is familiar to us. We're about to talk about, no, not here. In physics 2, you'll talk about electrons and protons and atoms. And you'll talk about the model of an atom, the Bohr model of an atom, where you have the nucleus of protons and neutrons and then electrons orbiting around it. We think of those electrons as little tiny points of matter. But in fact, they're actually waves. They're waves of energy that have something we call an electric charge. And we have this model, this picture of what an atom looks like, but that may or may not have anything to do with what we would actually see if we could get down that small. So models are just the analogies that allow us to visualize and thereby think about our theories and our laws. And that finally is the third word that you need to know, and that is a law. A law is only a law once it has been empirically confirmed. If it hasn't been shown experimentally to be true, it's not a law. It can still be a really great theory, but until the experiment is done, it's not a law. It is not, as some would say, scientific fact. Okay? Write this down. I know this sounds like a slogan, but it's still a good slogan. If it's consensus, it ain't science. And yes, ain't is a perfectly good word, a perfectly cromulent word. Okay, does anyone get that reference? I know you got it. I saw you. No one's ever heard the word cromulent before. Oh, man, I'm old. Go home and binge watch The Simpsons. You'll eventually run into it. Just wait till the semester's over. That brings us to measurements. And that was where I began. We're going to learn about measurements. Who here has heard of Lord Kelvin? Anybody heard of Lord Kelvin? Okay, just so I can make sure that everyone raise your hand. Okay. Raise your hand. I really, put it up. Thank you. I just want to make sure that they work. Eventually, somebody's going to raise their hand when I ask a question, and Lord Kelvin was a mathematician and a physicist and what else? A philosopher. The point is, he was not pigeonholed. Until the last century, all this notion of separating the fields of study into, well, this is chemistry and this is physics and this is biology, and it was all just considered science. It was any field of study where you could apply the scientific method was science. And this notion of specializing and segregation didn't exist yet. Kelvin was the one who came up with he worked in thermodynamics because they named a temperature scale after him. It's the metric equivalent of the Rankine scale. It's the scale where absolute zero is 0 degrees. And everything above absolute zero is some number of degrees. Lord Kelvin is the one who famously said that, and I'm going to paraphrase him here because I don't do quotes well. Unless I can read it, it's probably not an accurate quote. But paraphrasing, Lord Kelvin said that when we can quantify, when we can describe something mathematically with calculable precision, then we can say we truly understand something about it. Okay? That's when you get from philosophy into science, when you start talking in terms of quantifiable measurements. Okay? Up until now, you've all studied mathematics. You've studied algebra, you've studied trig, you've probably studied geometry. Some of you have studied calculus. Hopefully you have figured out that by now that mathematics is just a language. And up till now, what you've been studying is the equivalent of how to spell, how to conjugate a verb, how to use the correct punctuation, how to write complete sentences. Now, we're going to start using that language skill. Now we're going to start studying literature. We're going to see these physical phenomena that we observe in the world, and we're going to describe them mathematically, and hopefully you're going to see the elegance and the eloquence and the beauty of something that is so hard to describe, just concisely and succinctly written down in a simple mathematical statement. When you see that, that's when the mathematics starts meaning something to you. So, uncertainty. You need to know when you make a measurement, there is some uncertainty as to what you've measured. We take a ruler, a tape measure, and we measure how wide this room is from that wall to that wall. We cannot measure exactly how far that is. We simply do not have the technical capability of making a perfect, precise measurement. Everything we measure is going to have some degree of uncertainty. 4 of you, well, 3 of you that are here, wait, were you here for the lab yesterday? You're the one I can't remember. You're Ash, got it? Not Stephanie. You're Devon, got that? And Cyrus isn't here, but Kayla. And I am so sorry. I'm probably going to forget it again. And if it makes you feel any better, I'm probably going to forget theirs too. I just haven't forgotten them yet. Those who were here for the lab yesterday were measuring the period of a pendulum. And if you try to measure, okay, you set a pendulum swinging and you've got a stopwatch and you try to click, you try to measure it one period at a time, you're never going to get 2 measurements exactly the same. So what they had to do was measure 20 periods. Click, and then count out 20 oscillations and stop it. Now, the uncertainty was still the same. How far did they miss the absolute perfect apex of that first swing at T0 when they pushed the button? Because they didn't push the button when it was exactly at 0 velocity at the peak of that swing. They missed it by a little bit. And they missed it again when they tried to stop the clock. So they had this amount, this finite quantity of uncertainty built into the measurement, but they divided it up over 20 periods to make it smaller and smaller. They actually got some pretty impressive measurements of these periods over the whole experiment. They got some pretty consistent numbers, but when you repeat this experiment, you're going to notice that you might get 2 digits, but by the time you get to that 3rd digit, it's going to start changing. Okay, that means that's how much uncertainty you have. Now, there's a concept called precision and accuracy, and they're two different things. So I want y'all to be aware of these and think about these when you're working on these problems. Precision and accuracy. Precision is about repeatability. How repeatable can you make that measurement? Measuring the period of an oscillation. You measure it at 1.78 seconds. And then you measure it again and it's 1.74 seconds. Then you measure it again and it's 1.79 seconds. You've measured it to a precision of 1.7 seconds. And you might be able to statistically estimate something based on that third digit. But this has a precision of how many significant digits? 2, 1.7. Accuracy is a different thing altogether. Accuracy is about how close 1.7 seconds is to the actual time it takes that pendulum to swing. Okay? Now, in this case, the accuracy is going to depend largely on their reflex time, how fast they can respond, but it's also going to depend on the stopwatch. Okay, if the stopwatch is counting 1 second every 0.5 seconds, the accuracy is not going to be very good. It might still be very repeatable as long as it counts exactly 0.5 seconds every second. The precision might still be remarkable, but the accuracy is lousy. So, be aware of the distinction between precision and accuracy. You can measure something precisely, repeatably, 1.7 seconds, 1.7 seconds, over and over and over again, but accuracy means it actually is 1.7 seconds that you're measuring as 1.7 seconds. There's some exercises in your homework about significant figures. You can read about them in the text here. Years ago, when I was in undergraduate school, they said that if you measured, let's say you're measuring an angle. That's 30 degrees. 31, 32, 33, 34, 35 degrees, 6, 7, 8, 9, 40 degrees. You can look at the line here between 30 and 31 degrees, and you can estimate. That's about 30.5 degrees. You could probably estimate it to 1/10 of a degree, certainly to 1/4 of a degree, 0.25, 0.75. You might get 0.2 degrees of reliable estimation between there. Depends on how big the space is and how well you can interpolate. If this were your measurement, this would be 3 significant digits. Now, and this is where I was starting a moment ago. When I was back in undergraduate school, they would have said, this has an implicit uncertainty of plus or minus half of the next digit. So it would be plus or minus 0.05. That would have been the implicit uncertainty. Your book is going to tell you that the uncertainty is going to be much less well-defined. It's going to be plus or minus 1 or 2 of the last digit. Okay? And they're going to go through some exercises with you showing you how if you just go by strictly on the number of significant digits, then sometimes the actual percentage error is going to be quite different. What I want you to learn is that here you get 2 significant digits because the third digit keeps changing. Okay? Here you've got 3 significant digits because you've made this measurement diligently. And here's where we're headed. So don't fall asleep yet. How many significant digits is this? Here we've got 2. Here we've got 3. How many significant digits is this? Some of you might be tempted to say that looks like 4 significant digits, because you've made this very precise measurement, or this, hopefully very accurate, but at least very precise measurement out to 4 decimal places. That is not 4 significant digits. These are placeholders. Now, what makes this different than here? You've got an actual significant digit on both sides of the decimal point. Okay? So 0.0015 is very different than 1.0015. That would imply 5 significant digits. Okay? Now, when you start making measurements and doing calculations, let's say you measure this room, the length, you measure the width, and you know it within plus or minus so many half an inch on both ways. What's your uncertainty for the area of the room? Point is, when you multiply measured numbers together, you can never keep more significant digits in the result than in the smallest number of significant digits of any one of the factors. So if you multiply a 5 significant digit number by a 2 significant digit number, then your answer can only be 2 significant digits. Okay? The book's also going to take you through analyzing this on a basis of percentages. This is the last thing I want to cover. Scientific notation, because it will clear up this ambiguity, this almost deception here. If you wrote this number in scientific notation, it would immediately be clear that it's only 2 significant digits, because in scientific notation, you move 1, 2, 3, and it becomes 1.5 times 10 to the minus 3. You move the decimal place 3 places to the right. It becomes 1.5 times 10 to the minus 3. And there are your 2 significant digits. Okay? Has everyone here already worked with scientific notation? Anybody that this is new to? Okay, I suspected as much. If it isn't, I don't want to shortchange you on it. You're familiar with the standard prefixes, milli, micro. Okay, Good enough. Well, in that case, I think, am I mistaken? It's time to, it's the end of the class. So thank you very much. And homework assignment. Let's, wait here. I'll be right back. I want to get your homework assignment for you.